Hello, welcome back. So in the last session, we have seen what is 1NF, 2NF and 3NF, right? So we want to design our relation schema so that they have neither partial nor transitive dependencies, right? Because these types of dependencies cause update anomalies. That is why we want to disallow these types of dependencies. So the steps for normalization to 3NF obviously disallow these types of partial and transitive dependencies on primary keys, right? So the normalization procedure we discussed so far is useful for analyzing databases where primary keys have already been defined. So we are not considering any other candidate keys of a relation, if any. Okay, so in this session we will give some more general definition of 2NF and 3NF that takes all candidate keys of a relation into account. So definitely this won't affect our 1NF definition, right? Because 1NF is independent of keys and functional dependencies. Okay, so let us start with the definition of prime attribute. We have seen what is prime attribute. We define it as a part of a primary key, right? Now let us modify the definition. Any attribute involved in a candidate key is called a prime attribute, and all other attributes are called non-prime attributes. So we will define this partial and full functional dependencies with respect to all the candidate keys of a relation. Okay, so let us modify the definition of 2NF to give a general definition. Okay, so a relation schema R is in second normal form if every non-prime attribute A in R is fully functionally dependent on every key of R. Okay, so we are bothering about all the keys. So every non-prime attribute A in R is fully functionally dependent on every key of R. Okay, so every key means all the possible candidate keys. So let us take an example for that. So how will you test for this 2NF? We will take all the functional dependencies in a relation whose left hand side attributes are part of the primary key, right? And we will check out for any partial dependency. So if the primary key contains only a single attribute, there won't be any problem, right? There won't be any partial dependency. So let us take an example, the relational schema loads, okay, which describe parcel of land for sale in various counties of a state. And suppose there are two different candidate keys. First one is property ID number, and the second one is a combination of county name and lot number. That means the lot numbers are unique only within the county. That is why we are taking the county name also together with the lot number to define as a key. Whereas the property ID number is unique across different counties. Okay, for each and every property or land, the property ID number will be unique. So it can be taken as another key. And here the property ID is treated as a primary key. That's why it is underlined. But we have to consider the second candidate key also, county name, lot number combination also, when we consider the partial dependencies. Okay, so let us see first two dependencies based on these two keys. Okay, so first one, FD1 states that the property ID determines county name. Property ID determines lot number. So property ID determines all other attributes. Functionally determines all other attributes. That is the first functional dependencies. And what about the second one? The combination of these two, right? The second candidate key, that is county name and lot number together decide the property ID. And county name and lot number decides or determines area. County name and lot number determines the price and tax rate. So these are the functional dependencies based on this candidate key. Suppose that the following two additional dependencies are also there. That is the county name decides the tax rate. And the functional dependency 4 states that the area determines price. Okay, so we have two more dependencies based on the nature of this land. So the functional dependency FT3 states that the tax rate is fixed for a given county. That is why this function dependency holds. FT4 states that the price of a lot is determined by its area regardless of which county it is in. Okay, so area determines price. So these dependencies also there. So if we consider these four functional dependencies, this load schema violates the general definition of 2NF, right? Because we have a functional dependency from a county name to tax rate, right? Actually, county name is a part of a candidate key. It's a prime attribute, right? So we have a dependency county name, lot number, decide tax rate. So that was based on the functional dependency 2, right? And we have another FT3 which states that county name alone decides tax rate. So this is a partial dependency. So we are removing lot number, still a functional dependency hold, right? So this violates 2NF. So tax rate is actually a non-prime attribute which is partially depend on a prime attribute, right? Even if you are removing this, the dependency holds. So this is a partial dependency. So to normalize into 2NF, what we have to do? We have to decompose this original table, right? We have to remove the attribute which violate this 2NF definition. Okay, so we have to remove this tax rate from the loads into some other table. So we have created two different tables, loads 1 and loads 2. In the loads 1 we remove the tax rate from the original table. Okay, so and we have placed it in another table together with the attribute which created the functional dependency. Okay, so FT3 which was county name determines tax rate. So county name also we added in the second table. Okay. So now this both loads 1 and loads 2 are in 2NF. Now the general definition for third normal form. So we have already defined it based on transitive functional dependencies, right? Now let us modify the definition in a general way. So before that, a super key of a relation schema R is a set of attributes S of that schema R that contains a key of R. So any set of attributes which contains any candidate key of a relation schema can be called as a super key. Now the definition of third normal form. A relation schema R is in third normal form if whenever there is a functional dependency from X to A, X functionally determines A holds in R, then either X is a super key of R. This left hand side should be a super key, it should contain a candidate key, okay, or A should be a prime attribute. Any of the two conditions should be there if there is a functional dependency. Then only we can say that the corresponding schema is in third normal form. Okay, X should be a super key or A should be a prime attribute. Prime attribute means a member of any candidate key. Okay, so based on this we have to check whether our relations are in third normal form. So let us take the previous example. What about the loads 2? It's in third normal form because we have only one functional dependencies, right? And we have the primary key here, the county name. So county name determines tax rate, whereas county name is a super key. So this is in third normal form. And what about this loads 1? We have a functional dependency. Area determines price. Neither area is a super key nor price is a prime attribute. So this violates our third normal form condition, right? So this table is not in a third normal form. So we have to decompose this table to satisfy that condition also. How will you divide? So we will decompose this loads 1 into loads 1A and loads 1B. So we will remove this attribute, the price attribute, which actually violates this 3NF, right? So by removing that attribute, we will get the loads 1A relation, and we will place that price attribute together with the area. This is a functional dependency, right? So we have created second relation, that is lots 1b, with this price together with the area. So now both relations lots 1a and lots 1b are in third normal form. So this is the hierarchy of this decomposition. Initially we had only one relational schema, lots, which was in 1NF, first normal form. So in order to make it in second normal form, we decomposed that lots table into two different relational schemas, lots 1 and lots 2. Now both of them are in second normal form. Now we want to normalize it into third normal form. For that we decompose this lots 1 into lots 1a and lots 1b. Lots 2 is already in third normal form. So we have now three different relational schema, all the three in third normal form. So if we try to interpret this general definition of this third normal form, as you know, the third normal form, a relational schema can be told in third normal form if for any functional dependency x determines a holds in R, either of the two conditions should be there, right? First one is either x should be a super key or a should be a prime attribute. So if a relation is not in third normal form, that means both of these conditions are violated, right? So this happens because of two different types of problematic functional dependencies. So in those functional dependencies are there, then the corresponding relational schema will not be in third normal form. First thing is that a non-prime attribute functionally determines another non-prime attribute. In that case, this condition will be violated, right? So this catches third normal form violation due to some sort of transitive dependency. A non-prime attribute functionally determines another non-prime attribute. Like the second reason is that a proper subset of key of R functionally determines a non-prime attribute. So this is also an example for a violation, which is actually non-full functional dependency, or it's a partial dependency. So indirectly it violates 2NF. Okay. Based on these two observations, we can have an alternative definition for this third normal form. So a relation schema R is in third normal form if every non-prime attribute in R meets two different conditions. First one is, it is fully functionally dependent on every key of R. Every non-prime attribute should be fully functionally dependent on every key of R. That is the first condition. Secondly, it is non-transitively dependent on every key of R. Every non-prime attribute should be non-transitively dependent on every key of R. So if all the non-prime attributes satisfy these two conditions, we can say that the corresponding relational schema is in third normal form. Next one is Boy's code normal form, introduced by Boyce and Code. So BCNF in short. So we can say that the relational schema R is in Boy's code normal form if whenever there is a dependency, function dependency x to a holds in R, then x is a super key of R. So we remove the second condition for this third normal form. There we have two different conditions. Any one of them can be the criteria for this third normal form, right? But here it is a little more stricter. So we can say that the relational schema R in Boy's code normal form, whenever there is a functional dependency x to a, x always should be a super key of R. So each normal form is strictly stronger than the previous one. Just for example, 2NF is always stronger than 1NF. Third normal form is always stronger than second normal form. BCNF is stronger than third normal form. And obviously there can be relations that are in third normal form but not in BCNF, right? When we have a functional dependency from x to a in which x is not a super key but a is a prime attribute. In that case, that relation is in third normal form but not in BCNF. And BCNF considered to be definitely stronger than third normal form, right? And always the normalization we have to achieve at least third normal form. It's better to achieve up to BCNF. Okay, 1NF and 2NF are actually just stepping stone for normalization. We have to reach up to third normal form or BCNF. Let us see an example which is actually in third normal form but not in BCNF. Okay, so let us take the earlier example. In that we have already decomposed our loads relation into different schemas which all satisfy in the third normal form, right? And suppose we have set of counties, only two counties are there, and within the first county all the areas are of between 0.5 and 1 acres area, and for the second county suppose all the areas are of in between 1 and 2 acres. In such a situation we may have to add one more additional dependency, functional dependency, right? That is area determines county name. Okay, by seeing the area we can decide the county name. So if we add this additional functional dependency, that is FT5, still this relational schema is in third normal form, right? Because we have an additional dependency, area determines county name, where county name is a prime attribute, it's a part of a candidate key, right? So still this relation is in third normal form. But is this in BCNF? No, right? Because to be in BCNF, the area should be a super key, then only this will be in BCNF. So definitely we have to decompose this relation into some relational schema so that it satisfies the BCNF condition. So how will you change it into BCNF? Yeah, we will just remove this attribute which violated that BCNF, right? So county name will be removed from this relation and will be placed in the second relation. So county name and area will be placed in the second relation, and the other three attributes, those are property ID number, lot number and area will be placed in another relation. So lots 1AX and lots 1AY will be decomposed into two different relation schemas. Both are now in BCNF, right? But the problem here is that, what about FD2? County name and lot number together determines area, and county name and lot number together determines property ID number. Such a functional dependency is lost now, right? Because we don't have a coexistence of these different attributes together. So that is lost here. That's the issue. Anyway, in most relational schemas that are in 3NF are also in BCNF. So only in certain situations, that is x to a functional dependency is there, and x is not a super key and a is a prime. In such case only we have this condition, that is the relation is in 3NF but not in BCNF, right? And ideally the relational database design should strive to achieve BCNF or at least 3NF for every relational schema. Let us take one more example for this BCNF. So we have a relational schema with three attributes: student, course and instructor. This relational schema name is teach. And suppose we are taking student as A, course as B and instructor as C. So we have two different dependencies. First one is FT1, that is student and course together decide the instructor. Student and course together determines the instructor. And the second one is FT2, instructor determines the course. So these are the two functional dependencies. So is this relation is in 3NF? It's in 3NF, right? Because we have two functional dependencies. First one, FT1, X part is a super key. And second, FT2, the A part is the prime attribute. So this is in 3NF. And is it in BCNF? No, right? Because for FD2, the condition is violated. C is not a super key, right? So this is not in BCNF. Now how will you convert this into a BCNF form? Obviously we have to decompose this table, right? So what are the possible decompositions? Different possibilities are there. First one is we will divide this into R1 and R2. R1 with student and instructor and R2 with student and course. And second possibility, R1 with course and instructor, R2 with course and student. And third possibility, R1 with instructor and course, R2 with instructor and student. The problem here is that we have three possible decomposition, right? All the three, the FT1 will be lost. What is FT1? student and course together determines instructor. That will be loss, because to hold it, definitely these three attributes should coexist together in a single relation, right? That is not there in these three possible decompositions. You remember the case when we decompose something, two different properties should be maintained, right? We already learned that. What was those? First one, any functional dependencies which were there in the original table or original relation should be there even after decomposition. That was the first property. And second one is the decomposition should be always lossless. That means or additive join. That is, after decomposition, later we may have to join these different component schemas to get some information. We may apply some natural join and all to get information, right? Then, no spurious tuples should be generated. That was the second condition. And we also learned that in certain situations, we may compromise the first property, that is the functional dependency preservation may be compromised, but never the second property, that is always the decomposition should be lossless. No spurious tuples should be generated when we later join back these component relation schemas. So based on this, the third decomposition is the desirable decomposition, because it won't generate any spurious tuples after a join. So we can see how this can be tested, that is whether this decomposition is lossless or non-additive. Such things we can see later. Some algorithms are there. So for the time being, we can just ensure that the decomposition is lossless. Okay. So these are about BCNF. Thank you.